Hey everyone! Today we begin our quest to conquer reinforcement learning. Reinforcement learning is one of the coolest things you can do with neural networks, but what we're going to slowly see is the neural network is the least interesting part of reinforcement learning. And the only way this is going to make sense is if we start with some of the core reinforcement learning algorithms that have nothing to do with neural networks, right? The algorithms have existed forever. And so we're going to be exploring those one at a time going forward. But for today, I just want to set some context and give a little bit of a baseline of what are we doing, what is reinforcement learning, what are we planning on getting into, that sort of stuff. So let's go ahead and talk about a little bit about reinforcement learning and why it's a completely different mindset, especially for machine learning people. So for everyone that's been studying machine learning, our typical setup is this. We have some data, right? We have a collection of data. It's a CSV, it's a bunch of text, it's a collection of images, whatever it may be. And we probably have some label for those data, right? For each sample. And our goal is to train some model, neural network. It could be a standard machine learning model, any model. We want to train a model to be able to predict something given our data. And this works out because, as long as we have enough data, then we can train our model and everyone is happy. So again, this is a standard paradigm for machine learning. In reinforcement learning, this is completely different. We don't have data in reinforcement learning. There's no such thing as data in reinforcement learning. What we have is an environment. An environment is something that an agent, so you're the agent, or you can kind of imagine the model that you're going to be creating is the agent, and the goal of the agent is to interact with the environment. So the agent can take different actions inside this environment. And then the environment will produce a reward that gives the agent a reward for taking a specific action, right? That's the key idea. This is the feedback loop of the RL models. We have an agent, it takes an action in the environment then produces a reward with a reward function and gives it to the agent. And we're hoping that our agent can successfully navigate this environment by learning based on this reward function, right? So we want this agent to learn this environment, to be able to solve this environment and do well in it. And so why was RL so challenging for me personally? Number one, I jumped straight into deep reinforcement learning. When I started this, I didn't really put much importance or emphasis in more traditional reinforcement learning methods because I didn't think it was as important. But if you do this, if you jump straight into deep Q networks, for example, you have absolutely no context of where did this come from. Most of the time, you'll kind of just see the Bellman equation and be like, oh, okay, that makes sense, and then just keep going, right? There's nothing else. There's no foundation there that you've gained from just jumping into deep reinforcement learning. And what I want to explore, especially right at the beginning, is after we've covered a bunch of traditional reinforcement learning methods that have absolutely nothing to do with neural networks, you're going to see that the neural network basically doesn't add anything. It's the same algorithm. It's just a little bit different to be able to use a neural network rather than something called a Q table, right? So we're going to see, none of this needs to make sense here. We're going to see all of this in the future. But jumping straight into deep reinforcement learning is a mistake, I think. You don't have any context of what you're getting into. Because the algorithm itself, whether or not you're using a Q table or if you're using a neural network, the algorithm has not changed in any meaningful way. So this is one key thing to keep in mind. Also, reinforcement learning has like a lot of new terminology. There's model-based, model-free, there's values and policies, there's on and off policies, there's trajectories, there's advantages, there's just so many new words that show up in reinforcement learning, and some of them are subtly different and some of them are very different. So it just becomes a little bit of a challenge, and I'm going to do my best through the course of the next many videos to ensure that we define these as specifically as possible. So again, RL is a fairly challenging field, but what I've noticed from going through all of this over the last few years is that every RL algorithm is solving the exact same problem in slightly different ways. And what I want to focus on is, okay, like there's this algorithm and it solves it this way and it works pretty well, but there's some limitations here. Oh, this next algorithm solves those limitations in some specific ways. And what I want to show is the difference between algorithms, because fundamentally they're all doing the same thing. And so exploring it that way, I think, makes it a little bit more easy to approach and much more intuitive of what's going on. So first of all, what is an environment, right? The environment is essentially the bread and butter of your RL algorithm, which is really funny because we won't be spending any time building an environment. We'll be using some existing environments, right, from the gymnasium package, but yeah, we won't be building an environment. But if you are solving a real problem, you need to first create an environment that represents that problem, right? That's typically the hardest part, actually, and all the simulation folks get really excited about this stuff. So either way, the environment, let's kind of talk a little bit about what it is. It is a collection of states. And in this case, this is a typical problem that you're going to see in reinforcement learning, kind of, toy baby problems. And this is called the grid world. The grid world is basically you have 16 different locations here that you could be in. And what your goal is you're going to start at location 1. Your goal is to get to location 16 because that is your, treasure chest. It has all the stuff that you want. But there's some obstacles along the way, right? There's location 6, 8, 13, and 12 have little flames, right? So if you fall into a flame, game's over. So our goal is to get from the beginning, state 1 to state 16, while kind of working our way around these different flames. And this could be solved with other methods as well, right? We're going to be using RL, but there's different search algorithms, right, that would also be able to solve this. But today, for the foreseeable future, we're just going to be looking at RL for now. And so, yes, our environment is a collection of states, and this is called a discrete state space. Why is it discrete? Because there's only 16 specific locations that I could be in. There's also continuous state spaces, right? Continuous state spaces, it's the same idea, but instead of describing a state by like some, just like you're in this location, this location, this location, you describe it with some numbers instead, right? Like if you are on a map, right? On a map, you can have your latitude and longitude value. So every state is defined by the latitude, longitude, and this is continuous, right? Because these are actual numbers. So there we go. It could be latitude, longitude. We're going to be describing some more complicated states, like continuous states, when we go into some of the future videos. But for now, let's just keep it simple and just look at the discrete state spaces, right? Just to kind of set the stage here. But nothing really changes whether or not we're doing discrete or continuous. At every single state, there are specific actions that you can take. And so in this case, right, in grid world, your typical actions is up, down, left, right, right? These are the actions that you can take. And so our goal is to basically navigate this environment full of these states, limited to these 4 actions that we have available to us. And so this is typically known as the action space. And actions can also be discrete or continuous. We'll mostly be looking at discrete action spaces for basically everything, at least for now. We'll look at continuous action spaces later, but for now, a discrete action space is, you can either go up, you can go left, you can go right, or you could go down. Now, let's say you are training an RL algorithm to do autonomous vehicle driving, right? You want the RL algorithm to be able to drive a car. Does a car just say go left or right? No, of course not. It has I need to turn the steering wheel like this many degrees, right? How many degrees you want to turn. And once you go from a discrete action space like this one to a continuous one of how many degrees should I turn the steering wheel, then that now becomes a continuous action space. But again, to keep it simple, we'll be looking at discrete states and discrete actions for now. Our goal, right, is to get to the end, right? We start at the beginning, we take all these steps, and we get to our treasure chest. And that's our goal. But the problem becomes there are a lot of ways you can get from the start to the end. Here's one potential way of doing it, and this is known as a trajectory, right? This entire pathway we just took here is a trajectory. And a trajectory is basically defined as a set of states or set of actions that you took along inside your game until the game's over. So this is a trajectory that gets you from the start all the way to the end. So you've won this game. Another trajectory could have been you could have just like gone here and then fell into the fire, right? So this would be a unsuccessful trajectory because you didn't make it to the end, but it's still a trajectory. So the trajectory is just you playing a game until it's game over, whether or not you fell into a fire or you actually made it to your goal. But like I mentioned, there's lots of ways of getting to your treasure chest, right? We could also take this pathway, or we could take this pathway. We could go down, we could go here, but then we can kind of just loop around a couple times, right? This is completely fine. We're not breaking anything. And then after a couple loops, we go here, right? So this is another totally valid trajectory, but it obviously seems a little redundant, right? We're kind of repeating the same steps over and over again, but it's still a valid trajectory, and it is a valid path to solving the problem. So the question is, what is the best path? How do we find the best path? And so before we kind of get to that, let's first talk about the reward function, right? The reward function is very simply a function that gives you a reward based on the state that you're on, right? So the model, the environment, produces some reward. The entire purpose of the environment is to produce some reward given the state that you're in. And this reward function here is actually the one that's typically used in most of these grid world problems, where you basically get 0 reward everywhere, and then you get some reward when you get to your actual treasure chest, right? So this is typically known as a sparse reward function because, as you can see, there's really not a lot of information here. Like, if you get lucky to make it to the end, you finally have something to grab onto. It's like, okay, I know where the target is now. I know where I need to go, and at least have an example of me getting there. But when you're actually exploring this environment, this would be a very sparse reward function because there's nothing in this reward function that doesn't incentivize me to do something like that, right? We can just keep going around over and over again and get to the end versus just going down and getting to the end, right? Both of these pathways give me exactly the same reward, right? Just a +1 at the end. But obviously one is better than the other. And so creating a good reward function is an art form, right? So here is a slightly updated one that I just created, right? So reward mechanisms are an art form. And what that means is basically you need to have some intuition of the problem you're trying to solve. And you want to make sure you are incentivizing and disincentivizing the things that you care about. So what you have here is a -0.1 at every single state and a -10 on the fires. So what am I incentivizing this way? Let's take that pathway again. If we go here and kind of spiral around a bunch, right, and then get to our answer versus just go straight to the answer, what do you notice? When we spiral around a lot, we're going to collect a bunch of -0.1 rewards as we're spiraling. And this will give me a large negative reward, which isn't good, as we're doing it. So this reward mechanism would tell our model that, hey, this pathway we just took is no good because we're just collecting or accumulating up a bunch of negative rewards as we're kind of circling around. On the other hand, sure, we are collecting some negative rewards as we're going here, just not nearly as many to get to the state. So this is an example of slightly improving your reward mechanism to incentivize taking a shorter path to your final destination. I've also put heavier negative rewards on these flames because we want to make sure that, hey, if you touch the fire, game's over. We don't want that at all. And it would disincentivize getting anywhere near these fires. Right, so again, the reward mechanisms in art form, you typically have to play with them. Everyone I know doing RL research on like custom environments, they spend a ton of time trying to think through reasonable heuristics for this stuff. But again, there's no hard and set rule. It's mostly trial and error. But again, you want your reward mechanism, your reward function, to incentivize the things that you want and disincentivize the things you don't want. Right? And that's the key idea that I want you to take away when it comes to these reward models. Now, we won't be writing, again, any of these reward models. We'll be using existing environments that already have their own reward function. But of course, if you wanted to update them or create your own, well, here you go. You'd have to kind of think through what is it you want, what is it you don't want, and somehow numerically represent it as you see here. So our goal is to get to the end, right? Our goal is to get to the end, get to this treasure chest. But again, how do we do this? So let's kind of think through a couple of steps that's necessary to get to this point. Number one, let's define a new word, the policy. The policy is the thing that determines your action. It says, what action should you take given the state? In this case, our actions are up, down, left, right, right? Those are my 4 possible options that I can take at every single state. And the policy can be 2 things. It can either be it can either pick a single one, like at this date, you should definitely go down. At this date, you should go left. At this date, you should go right, ... right? You could either do that, or you could have a distribution. You can say at this state, the probability of you going down should be this much, and the probability of you going up should be this much, so on and so forth. So that's your stochastic versus deterministic policies. For now, we'll be looking at deterministic ones because we're just going to say at this date, I want exactly this action. But you could also have a stochastic policy where you say at this date, you should take this action, like with this much probability, but there's some other actions that you could take with other probabilities. So that's your stochastic versus deterministic policies. But yeah, either way, that's kind of a detail we're not going to worry about just yet. And so yes, the policy prescribes the action you should take at the different states. And this is our output of the RL algorithm. Like, this is the thing we want at the end, right? This solves our environment. We're hoping a good policy can tell me the correct set of actions to take at every single state to get to my answer. That would be a good policy. So this is our final output. But this is a clear misconception. The policy is not what we're solving for. And the way you should consider this is that our model, the thing we're training or the thing we're building, does not determine what action I should take at every state. We will find the policy afterwards. Like, the policy is the final output of our RL algorithm, but it is not what we are solving for. And this is a little bit weird to think about, but it'll make more sense as we start exploring it step by step. But what we're not solving for is this. We don't care right now about what action should I take at every state. Instead, what we want is to maximize the future rewards. That's the actual question that we're trying to answer. And so what do I mean by future rewards? What I want to know, and this is known as the value function, which we'll see again a little bit later, but the value function, V, tells me what is the value of this state. What is the value of this state? What is the value of this state? And what these values are is our expected rewards. It means that if my agent happens to find itself at V3, what can I expect to get as my rewards if I'm here, right? That's it. So what can I expect to get as my rewards here? And we're going to look at exactly what that expectation looks like in a little bit, but that's basically the main idea. If I find myself here, what can I expect? How can I expect to do in the future? Right? That's the key idea that I want you to take away. We're maximizing a future reward rather than just trying to predict what action I should take at every state. Again, we're going to look later. For now, we'll be doing value-based models, but there are policy models too. These are called policy gradients, but we won't be seeing that until much later, right? When we start looking at the reinforce algorithm, as well as TRPO, PPO, actor-critic methods, and other stuff. But for now, we are not looking at models that solve for the policy. We're looking for models that solve for the value, that can determine the value of every single state. And then once we have determined the value, then all I need to do is whenever I'm here, I will go to the value that is higher, right? If I know that going here has higher value than going here, then I will move this way. And then here, obviously the only options I have really is to go down, so I'll move down again. And I'll essentially determine, again, when I'm here, is it more value to go to this state or is it more value to go to this state? I don't know, right? That's what our model will be solving for. But once I have that, I'll say, oh, it's more valuable to go down this way, so on and so forth. So our first step is to solve this thing known as the value function. So before we get into the value function, let's talk a little bit more about the rewards. What do I mean by future rewards? I'm saying maximizing future rewards. What does that exactly mean? The value of this state here, let's just look at it for one trajectory. The value of this state here, or the reward that I got for this state here, is this entire trajectory. So what did I get on so I went from state 1 to state 5, and then this is 9, 10, 14, 15, right? Those are my, because it's 1, 2, 3, 4, right? Those are my state numbers. So what I've done is I've completed this trajectory in this case, and I've accumulated some reward for all those different steps, right? That's the key idea. We've accumulated this reward for all these different steps, and so we have all these negative 0.1s. And this here is known as an experience tuple. An experience tuple is essentially, what is my starting state? We'll call it S, right? That's where I'm starting with. What is the action I took at that state? We'll call that A. What is the reward the environment gave me for the action? We'll call that R. And then what is the new environment I ended up in? That's S prime, right? So this here is known as an experience tuple. Your state, the action you took, the reward you got, and then the new state that you ended up in. And so what we could do first is play the game once, right? And we've collected this trajectory here. Play the game and just keep track of your experience tuples. Just store it. Store it as literally a list of tuples is what we're going to see it ends up being. And so now we have some data. We have some data to work with about our environment, an experience that we've collected from our environment. But what do I mean by future rewards, right? In this case, right, in this trajectory, this state here, okay, so let's actually go into the next one. When we're doing future rewards, there's two ways to do, there's actually two ways to do it. First of all, I could just say that the reward, I got this trajectory from this state here, so state 1. So in this case, the future rewards of state 1 will be negative 0.1 plus negative 0.1 plus dot, dot, dot. We're going to add them all together. So this is just going to be 1, 2, 3, 4, 5. So it's negative 0.5 plus 1. So that's just going to give me a 0.5 reward at the end. So all we've gotten is a 0.5 total accumulated reward for this trajectory. But this assumes that my reward for my next state is equally important as a reward for a much later state, right? So we're saying that this reward right here, which is many steps later, is just as important as this step right here. And so there's no real balance here. And so the first step is determining the balance between your current rewards and future rewards. And so this balancing act is typically known as the discounted reward. So what is a discounted reward? It's essentially just an exponentially weighted sum of your rewards. And so gamma here is typically between 0 and 1, right? That's your range. And so let's kind of think a little bit about what's going on here and understand, why do we balance rewards? What's the point of balancing? Let's say, you're a student, you have sat down and you're learning about reinforcement learning now. You're looking at this video. Do you feel like you're going to get an immediate advantage, an immediate benefit of learning some of this stuff tomorrow or an hour from now? Probably not, right? There's no immediate gain that you're going to get from learning reinforcement learning in the next day or so. Probably not. On the other hand, if you keep at it, you know that learning reinforcement learning now could have some meaningful impact in your ability as a machine learning engineer or a researcher or whatever in the future, right? Maybe a few months later, an opportunity will arise where you can leverage this knowledge and then actually use it, and then you get the gain. And so this is a clear idea that most humans deal with, right? We're balancing our present rewards, our present gains, and the future. If you think about it, if you're on a weight loss journey, you can either have the cake now, and because that's an immediate gain, right? Immediate gratification for the current, or you could not do that and get some different reward in the future, right? Like losing weight or something like that. So this clear balancing act between your present and future rewards is something humans deal with all the time. And the idea here is we just want to codify it in some mathematical way, and doing an exponential decay is the way. And so what this will kind of look like is that we could have a graph here. Let's say we have a high discount value, so close, let's say 0.99. So what we're going to do is we're going to basically start at 1, right? Because 0.99 to the power 0 is just 1. And we'll slowly decay our thing, right? So this is going to start at 0, and it's going to go to t, right? 0 to t. And so what we've done here is ensure that, okay, we are giving more weight to the beginning states, but we're still giving some weight to later states, right? So we're giving some weight to our history. So we're giving some importance to future rewards. And so this would be kind of a good balance of I want to put more weight, more incentivization on doing better on these initial rewards, right? Because I need to make sure that my current actions at early states are good, but I want to also put some focus on what I could hope to gain in the future. Similarly, right, if we pick a small value, a small discount value, then you could end up with something like this. You'll very quickly decay. And so in this case, we're putting emphasis on our early parts, but basically no emphasis on the future. And so we're not really putting much weight on the future rewards that we could hope to gain from the actions that we're taking. And so this balancing act kind of depends on the problem that you're dealing with, right? Or do you care more about current rewards and what happens in the future isn't that big of a deal? Or vice versa, do you really need what happens much later in the future to matter more than what's happening now, right? And this balancing act does matter. And here's an example, right? If you're training an autonomous vehicle and you're driving down a street, then you want to make sure that while you're driving down that street, you get good, you want to make sure you're putting good amounts of weight on that reward. But how I'm driving on the street right now on one road doesn't really affect the reward I'll get on another road, maybe an hour later into a road trip, right? So how much incentive you want to put on current rewards versus future rewards is exactly this balancing act that you have to play with. Again, this is a hyperparameter, right? It's something you have to mess with and see what works, what doesn't. So here's an example, right? Kind of a written out example. Let's say we pick a discount of 0.9, gamma of 0.9, and a discount of 0.5, right? Two different reward functions. Reward weights are for exponential decay. Well, here's the rewards that we got earlier, right? Lots of negative 0.1s and then a +1 at the end. And you can see that with a higher gamma, we have a slower decay. So even at our last state, we're putting our last time step on our trajectory, we're still putting a reasonable amount of reward on our rewards, right? We're putting a reasonable amount of weight on our rewards. On the other hand, when we have a smaller discount, we can see the weight has gotten much, much smaller, right? It decays much faster. And so this is, again, just something to keep in mind of how much do you want to care about future rewards versus current rewards? And this is just a clear balancing act for most reinforcement learning problems, but it's just a balancing act of regular life, right? We're always trying to determine if I take this action now, am I going to immediately get some gain from it? Am I going to get some gain from it in the future? And the gamma, the exponential decay, is how we effectively just, convert it to like a mathematical representation rather than just feeling. Okay, so that's step one, right? So we understand the reward mechanism now. And so all we're doing now is we're going to play a game. We're going to collect a trajectory. We're going to keep track of the rewards we got. We're going to exponentially weight them by some discount and then add them all together. And that's how we determine our kind of the discounted reward from a trajectory. Now let's go back to what we were talking about initially, the expected future reward. Our goal is to maximize, our algorithm's goal is to maximize for every state the expected future return. That's our goal. That's what we want to learn. It's not, oh, what action I should take at every state. It's what is the value of a state, the expected future return of a state. And so what we need to do is at every single state, like you see here, we need to compute the value function. What is the value of these different states? And so this is a little bit weird, and this is probably the hardest part about reinforcement learning to wrap your head around, because we want expected future return. What does that even mean? What is an expected future return? So first of all, let's look at the formula for the values before we kind of keep going. The values of a state is the expectation of GT. So what we have here, remember GT is our discounted rewards. It's the expected GT. It's our expectation for GT, given that we're starting at state S, right? Whatever state we're in. So what we're going to do is let's just take one of the states. For one of the states, we're going to grab a bunch of trajectories, and we're going to compute GT from all of them, and then average it together. But there's a little bit of a problem with this setup. Imagine it this way. What I want is the expectation is over all trajectories, right? Trajectories of GT, right? That's our goal, given that we're starting at. So let's say we're starting here. How many trajectories can you think of starting here? We can have this is a trajectory, and this is a trajectory, or 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 sorry, this is a trajectory, this is a trajectory, ... Like there are lots and lots and lots and lots of different possible trajectories that you can draw from one to game over. You could even have one that loops over a bunch and a bunch and a bunch of times and then ends up here. And so this is a problem. Even in a simple environment like this one, where we only have 16 states, we could reasonably come up with lots and lots and lots of trajectories. But what the idea is that we're going to basically grab all of these trajectories. I'm going to compute GT for each of those trajectories. So we'll call it GT for the first trajectory, GT for the second trajectory, GT for the third trajectory, ... We'll have GT for, let's say, the P possible trajectories that are available to us, right? That's our list of all the different discounted rewards we got for all the different trajectories that we just went through. And then we just average them together, right? We'll take the average of this, right? We'll take the mean, right? So this process sounds ridiculous, right? It sounds ridiculous, right? There's no way. Imagine if our environment had 1 million states in it. There's just no way that I could for loop through every single trajectory possible and then compute the discounted rewards for each of those trajectories, and then average together all those results, only to compute the values of one of them. And remember, we have to repeat this operation for every single state in our environment. It's crazy, right? There's just no feasible way of solving this if we did it this way. And this is why we will use a method called dynamic programming. So dynamic programming, a lot of people, most CS people don't like it. Most people, they find it kind of annoying, and it is kind of annoying, but the main takeaway for dynamic programming is that you take a problem that you have and you break it into a bunch of subproblems, and you use the accumulated information kind of for different things. So for example, if we're computing all the trajectories from here to everywhere else, right? This and all possible trajectories. Well, one of those trajectories is going to include this one right here, which means I could also compute the values for this state and use that information in this other one, right? So there's a lot of, you can imagine when you're computing all the trajectories, there's going to be a lot of overlap between the different trajectories for the different starting states. And so instead of recounting those overlaps over and over again, because it's not like the values of the returns or anything change. It's the same computation, just overlapped in a different way. So instead of repeating that operation over and over again, why not break our problem into a bunch of subproblems and just ensure that we're not computing the overlaps? And this is essentially what dynamic programming does. And dynamic programming turns this intractable, try every single possible combination possible, to a feasible problem. And it does this using something known as the Bellman equation, which is a dynamic programming method to efficiently find the values for all states. Now, when I first saw this equation, it honestly confused me. There's like a lot of stuff going on here. And so today I'm going to give you just the general high level of what's going on, get some intuition for the pieces of this function. But next time we are going to derive where this even came from. So we're going to do the full proof of where this came from. And the proof is really not that complicated. A couple of little tricks here and there, but it's important to kind of understand where it's coming from. So just keep that in mind. Today we are just focused on getting some intuition for what's happening. But either way, this is a dynamic programming method, and it utilizes recursion. Why is it recursion? Because notice here, our value of a state. Okay, so let's actually define some stuff before we keep going. S is our current state. So current state, right? A is our action. R is the reward we got for that action we just took. So that's the reward we got. And then this S prime is our next state, right? Next state. So basically, just like we had earlier, this is our state 1. We took this action, we got this reward, which is little r in the formula, and then we have our next state 5. So there we go. So this is our very standard setup. This is the very standard Bellman equation. And the most critical part is every single RL algorithm is just solving this equation in a slightly different way. And so we're going to basically come back to this over and over and over again, which is why it's important you really understand what's going on. So let's deconstruct this a little bit. So first of all, notice the recursion. Our value at state S depends on the value at the next state, S prime. Okay, so we have basically our function is being called inside itself, which means it is a recursive function. And this is how we solve the subproblem. I know that the values of this state, all the trajectories, right, that I could have taken from the state, has some overlap with all the trajectories I could have taken from this state. And so by recursively solving it, it allows us to essentially not recompute stuff that we had already done. So first of all, we have this recursiveness in the Bellman equation. So that's step 1. The values is computed by averaging over all the actions you can take at a state. So remember, this is our policy, right? Policy. And the policy prescribes an action you take at every state. And there's kind of 2 ways to go about this. If the policy is deterministic, like the ones we are going to be dealing with, then this is basically just like, you can imagine if we have left, right, up, down. In a deterministic policy, let's say at this state, it's recommending to go up. Then you'd have 0 probability everywhere, but 1 probability, 100% probability on up, right? 1. Sorry, so 1. Let's clean that up a little bit. Here we go. 1. Okay. So we have 0 probability every and 1 on the action that we take, which means when we're summing over this action space, right? It's basically going to be this pi or policy at a given 0 is going to be 0 everywhere and just 1. So it's just going to keep 100% for the action that we care about, and really all we're left with is this stuff right here, right? So that's kind of for the deterministic policy. But we could also have a stochastic policy where we say this is 0.2, this is 0.1, this is 0.4, and then this is 0.3. So now it'll be kind of like a weighted average of, okay, it's going to be 20% of if I take this action, and 10% if I take this action, and 40% if I take this action, right? For all the different actions you can take. And so this would be a stochastic policy where we're predicting the probability of the different actions that we take. Again, for now, we're going to be dealing with just our deterministic ones, but later we'll get to stochastic policies as well. So this is basically just an average, a weighted average over the action space. And the weights in this case are the probabilities. In the deterministic case, it's 0 everywhere and 1. So it's a 1 hot encoded for the action you want. Otherwise, it's, this. So there we go. That's step 1. The value is computed by averaging over the actions you could take at that state, which again makes sense because at, let's erase a little bit of this so we can see again. There we go. Right, because my trajectories here, right, my trajectories could be, I could go this way and I could go this way. I mean, I could go up or down or up and left, but obviously there's no up and left right now. So for now, let's just look at these two. We could go this way, we could go this way, and that's it. In these environments, that's actually a good thing to point out. If you try to go up, it's basically nothing happens. You just get the reward of the state that you're currently at. If you try to go left, then again, you get the reward of the state that you're currently at because you can't leave the boundary of the game, of course, right? So there we go. And so when we do this, we want to average over all trajectories, but there's 2 directions our trajectory can even start from. So we need to average from those starting directions for those trajectories. And so that's the step 1, right? Values is computed by averaging over the actions you could have taken at that state, which is determined by the policy. After that, after we take an action, right, we will end up at a new state, right? We'll end up at some new state and we'll get some reward for being at that state. And so what we're going to do is add up, right? We're going to add up our current reward that we got for the action we just took, right? The current reward we got for the action we just took. And it's again determined by the reward function of the environment, plus a discounted value of the next state, right? And this is the crucial idea. We have discounted again with the same gamma, the values of the next state. And so this is basically solving our problem recursively. So if we go back again to here and erase some of this, our value at this state, so value here, is going to be, if I go in this direction, for example, it'll give me the reward of this state, which we'll call it R, plus our value of also being at this new state, S prime, right? And we want to make sure we discount it because future rewards are discounted. We want to make sure that future rewards, we have some gamma factor that lets us weight how much of the future reward do we want to keep, how much do we not want to weight it, so on and so forth. But remember, the value of this state is also dependent on all of the possible trajectories that it can take. And so when we, again, compute the value function for this new state, let's go back. When you compute the values for this state, it again will depend on it'll be a weighted average over all the actions you can take, but then it'll be also dependent on the value of the state after that. And we're basically recursively going through all of the different states and looking at the next step, the value of the next state, given the action that we took. So this will make a little bit more sense when we actually derive the Bellman equation next time. But that's the key idea. Remember, the values is my expected return, what I can expect to get if I'm at that state. And so the value of my current state is basically the reward I got from taking that action at that current state, and then adding to it the reward I can expect, because again, this is the reward we expect to get. So I add it to a discounted reward I expect to get at the future state. And this is a key idea that you really need to understand, because if you don't understand this, then basically everything going forward won't make sense. Again, when we derive the Bellman equation, you'll see where this recursive relationship actually shows up, and then it becomes very obvious of why this works. But that's the key idea. The value of my current state is basically the sum of the reward I get for an action plus the value, the expected value the next state would have given me, right? And we recursively solve it. Because remember, to solve this, I can't just, I don't know, first of all, I don't know what v pi s is, right? I don't know what the value of s is. I also don't know what the value of s prime is, which means I need to recursively go deeper and deeper until I get to the end of the trajectory, right? Just keep going until I get to the end, and then I backtrack back to my standard recursion setup. So again, we'll see all of this kind of very slowly for this first implementation, because I really want to build it up. The last part is we weight this, right, by the probability that we got to S prime to begin with. And this is a little bit different because we actually haven't talked about this yet, but we talked about the stochasticity of a policy, right? You could have a probability distribution of your policy. You could have different probabilities of, oh, you should go 20% left, 30% up, so on and so forth. What we haven't talked about yet is the stochasticness of the environment. The environment can also be, actually, most environments are random, right? If you are training an autonomous vehicle, there's going to be random stuff that happens, right? A person runs into the middle of the road, a car cuts you off, all sorts of random stuff can happen in the environment. And so what we need to do is ensure that we average over all possible states we get to. So let's kind of take a look at this. Why wouldn't we get to S prime? If I decide that I'm at this state and I want to go down, then why would I not go down? And this is because environments can be stochastic. So in the frozen lake environment, which is one example of the grid world environment, the frozen lake environment, the floor is icy. So your agent can intend to go down, like we could go down, that's what we want to do, but it could accidentally end up going left or right. And this makes it a stochastic environment, because even though I intended to go down, I ended up not going down. I ended up going left or right because the environment pushed me that way. And this is just randomness, right? There's always randomness in any reasonable environment. And so we have a problem, right? So like we intended to go down, but we ended up falling in the fire. So this is not good. So this means that we need to understand, or we need to weight by the probability of getting to a state. So in our case of the frozen lake environment, if you intend to go in one direction, you will go in that direction 1/3 of the time. This is I didn't come up with this number. This is the environment, right? This is how it's set up. That's how they built it. So 1/3 of the time, you will actually go down. But 1/3 of the time, you will go left, or 1/3 of the time, you will go right. So basically, if you intend to move in one direction, you could equally likely end up going in one of the perpendicular directions. So you won't go backwards, but you'll go in one of the perpendicular directions, right? So if you want to go down, you'll end up going this way. If you wanted to go this way, you could end up going in one of these two directions, right? So this is the stochasticness of the environment. And so when I say that I will average up, and this is why we have a sum over the states and a sum over the rewards. Because when I take this action at state S, I may not necessarily end up in the environment that I want to be in, or in the state that I want to be in. My S prime may not be what I want it to be. My S prime could be one of my other possible states that I could end up in. And so we need to average over, right? So this is the weight, right? What is the probability of ending up at that new state? Because I have a 1/3 chance of ending up at any one of the possible places that I could want to go to, right? I have a 1/3 chance of getting into any of these S primes. All of these are valid S primes. So I have a 1/3 chance of getting into them. And so I need to add up across my states and my rewards, right? And just weight my future expected reward, right? My reward plus my future expected reward, discounted future expected reward, weighted by all of the different states I could have ended up in. And this is just a crucial idea. So we've basically included here a stochastic environment, a stochastic environment where we average over all the possible places we could be. Okay, good. Yeah. So again, I'm trying to relate here some of the math. Again, this will make a little bit more sense when we actually derive the equation. But for now, I hope this is a little bit clearer of what's going on. So as a recap, let's just erase all of this. Let's just recap exactly what's going on from the start so it's very clear. I am currently I want to find the value of state S, which is my expected discounted reward of all the possible trajectories I could take from S. What that means is from state S, I can take an action, right? Any action, up, down, left, right. And my policy of that action could be one hot encoded, where like, oh, you definitely go left or you definitely go right. Or it could be a probability distribution of, with 20% chance you should go left, and with 40% chance you should go right, so on and so forth. But we're basically doing a weighted average with our policy as the weights for the different actions we take. But in a stochastic environment, when we take action A, we may not necessarily actually get to the state S prime that we wanted. Even though I want it to go down, I might end up going left or right because that's what the frozen lake environment is. So what we're going to do is sum over, do a weighted sum again, over all the possible states I could end up in and all the possible rewards I could have gotten for those states. And I'll grab my discounted rewards, my current reward, plus discounted future expected rewards, what I expect to get from the next state going forward. So these are the GT from S, and then this is GT from our next state, S prime. And I discount them, right? Because we want to discount future rewards. And I weight them by the probability of getting through those states to begin with. And that's the key idea. In this case, it's kind of perfect. It's 1/3 everywhere, but it could have been like, oh, if you go straight, you're most likely to go straight, but you might slip left or right. So again, this is just a very key idea for stochastic environments. So this is, again, the Bellman equation. Because the environment is stochastic, we need to weight by this probability. And something that I want to mention is the relationship between values and Q values. They are exactly the same thing, with just slightly different terminology. So a value is the expected rewards of a state, right? What I can expect to get in the future. And the value is just our Bellman equation. But the value is a average over the actions we take. A Q value, on the other hand, that we're going to see later, a Q value is the value of being in a state and taking an action A. So you can imagine that this is basically like marginalizing. If you have some probability distribution of some joint distribution of X and Y, and you sum over Y, then you're just going to end up with the probability of X, right? We're just marginalizing distribution. And that's exactly what's happening here. We're basically just summing over one of our joint distributions of S and A. We're summing over the actions to get S. Or basically, we're just taking an average. So our values, the value of a specific state, our future rewards that we expect to get at a specific state, is just the weighted average of the value of taking a specific action at that state. And again, this will all kind of make sense later, but this is just our Q values here. So when you see like Q learning, deep Q learning, this is basically what we're dealing with, this part right here. Right, so now next part, there are two types of models that we can have. Or basically two types of environments that we can have. We can have model-based learning, where we have the model, the Markov decision process of the environment. And MDP, if you've never heard of them, they're pretty simple. Is basically you have a set of states, and there's a set of actions that we can take between them, and we have some transition probability of reaching a new state from the current one. And so if you've ever seen those kind of Markov processes, right, you'll have some state like this, and you'll have some state like this, and you'll have some state like this. And then we have some transition probabilities kind of between the different states. Like, oh, this is 50-50. So going from 1 to 2 is 50%. And going from 1 to itself is like 10%. And then going from 1 to 3 would be, so that's 60, so 40%. You'd have to go through and add all of them in. But basically our transitions between the different states is our MDP, right? If you have this matrix of transition probabilities, which we're going to look at in more detail later, then you have the Markov decision process. You have the underlying statistics of the environment. And if you have that, there's actually a lot you can do without needing to do much. So if you have the transition probability matrix, if you have the model of the environment, then you actually never need to even interact with the environment, because everything you need to know about the environment is already inside that model. It's in this transition probability matrix. So this will be the very first thing we implement, these model-based methods where we have the MDP available to us. So here's an example of a model-based learning for a deterministic model. So in deterministic models, we're going to have, what is the state that we're at? So again, this is what our gymnasium gives us, but it's just a dictionary of stuff. We have the state that we could be at, so we're at state 1. And if we took action at state 1, we're going to get to a next state, right? What's the next state we'll get to? What is the reward we'll get for that state? And is this the end of the game? So game over flag. And because this is deterministic, so this is not a frozen lake, it's just a regular like floor, right? So if you walk, if you want to go down with 100% probability, you will go down. This is a deterministic environment. If you want to go down, you're definitely going to go down. There's no randomness of, oh, you might slip and go left or something like that. So if you take a state, if you take an action at that state, this is the next state you're going to be in. This is a reward you'll get, and you have a done flag. And it'll give you a probability, but the probability is just 1, right? Because with 100% probability, you're going to end up at the state that you wanted to get to. On the other hand, in a stochastic environment, you'll have, I'm at a state, there's an action I take, but from this action, I could, let's say the action is go down. I could either end up in the environment under me, I could also go to the one left, and I could also go to the one that's right of me, right? My 3 options. If I want to go down, but I don't actually go down, these are my 3 options. And then these are the probabilities of getting to each of these states. In our case, they were all 1/3, right? Very simple. You also get a reward for those different things. In our case, if you remember, if we go down, we'd get the reward of this state, which would be negative 0.1. But if we fell into the fires, it'd be negative 10, right? So there we go. And let's see here. Okay, so yeah, so that's it. And then again, game over. So if we had gone left or right, these 2 done flags would be true, like it's game over. And again, at this state, we could have taken a different action. What if we wanted to go up? Well, if you wanted to go up, then you'd end up with, you know, a different set of probabilities. So there we go. Okay, good. On the other hand, there's something known as model-free learning. Model-free learning is where you do not have the environment. You don't have the Markov decision process. All you have is the environment that you know nothing about and your agent. And the only way to learn about this environment is by interacting with it. So you have to essentially interact with the environment, play the game over and over again, and hopefully by playing the game sufficiently enough times, you'll be able to understand kind of, oh, where are the bad things? Where is my target? Things like that. And so this is model-free learning, where you know nothing about the environment, and the only way to solve it is by interacting with it and collecting information. And so there's a lot of ways of doing model-free learning. The first one is the Monte Carlo method, which will be the very first method we look at when we move to model-free. And so the Monte Carlo method is essentially just go ahead and play the game until you get to the end. Or, you know, in this case, the end is just the treasure chest, but the end could also be one of the fires, right? Just play until you've ended the game. You're done. So this way, you'll end up having kind of a full trajectory, a full trajectory of the game, and you can use that to make lots of different estimations that we're going to talk about in the future. So this gives you a good idea, because if you play the entire game, then you have a good idea of what's going on in the environment. But you could imagine that if your environment was very large, like let's say you have millions of states that you could be in, playing an entire trajectory before updating your beliefs of the values and stuff like that, that could be fairly expensive, because every forward pass, every like collecting a trajectory could take a while. So this is kind of expensive, because although we have real world information about the environment because we've played a full game through this environment, it's slow. It's a slower method of doing it. So there's kind of this, trade-off that we have here. On the other hand, we have something called TD learning, temporal difference learning. So we're going to look at this again. In this case, what we're going to do is we will update our beliefs, update our values as we are interacting with the environment. So instead of just waiting to the end to say, aha, this is what I should do, instead we're going to update with kind of the minimal information we get at every single iteration. So this allows us to quickly get better, right? So it allows us to more quickly update our model. It uses a method from statistics called bootstrapping that we'll talk about later. But these are basically bootstrapped estimates. But because we are using partial information rather than a full trajectory, you would imagine that our estimation of like what's going on in this environment is not as good, right? Because in this case, we played a whole game, so we know we have more information before we do the update. On the other hand, if we update at every step, we have less information at each of those updates. And so it's just not as good. But TD learning is essentially the bread and butter for most RL algorithms today because it seems to work out really well. Lastly, right, another key idea is exploration versus exploitation. So we haven't talked about this yet, but in the case of model-based learning, like I mentioned, there's really nothing to do. You have the environment, you have the transition probabilities, you have everything you need. And so if you have everything you need, then you don't need to interact with the environment. But now in model-free learning, we actually need to explore our environment. And this leads to an exploration versus exploitation kind of trade-off. And basically the idea is very simple. When you've initially started training, right? So when you're initially building your model, you haven't played the game yet. It's better to take some random decisions and just explore the environment. If you know nothing about the environment, then you might as well just randomly explore it. And hopefully you'll be able to gather enough reasonable information to learn something from it. On the other hand, as you're getting better and better at the game, then you're better off actually utilizing the information you've learned, right? Utilize the policy you have or the value function you've learned and start exploiting what you have. So again, it's just a balance of exploration versus exploitation. You're either randomly trying some things just to gather some more information about the environment, or you're using the information that you actually have and use that to follow your policy that you've ended up learning and try to solve the environment. So again, there's a lot of balancing acts when it comes to RL, and this is just another one. How many random actions do I want to take so I can maybe end up finding a better way of going to my trajectory, getting to my final answer? Or how many times do I want to actually use the information that I've collected and make a data-based decision of what action I should take? So it's just, again, a trade-off. And typically when it comes to these trade-offs, we have some kind of middle ground that we'll be implementing. So finally, the plan, right? There is a lot of stuff that I want to cover. Mainly, what I want to do is we're going to first start with the derivation of the Bellman equation, because if we really don't do that, there's not a lot of context of what we're going into. You don't necessarily need to know the derivation of the Bellman equation, but it's not a particularly difficult derivation, and I think it just solidifies a lot of stuff that will show up over and over and over again. So once we've derived the Bellman equation, we're going to start with two of the most common model-based methods, policy iteration and value iteration, right? So this is the example of we have the entire Markov decision process, but there's two ways of solving the environment when we have the MDP. We can do policy iteration or value iteration. All of this is going to make sense later. Then we're going to move into methods where, hey, we don't have let's say we don't have it. We don't have our model. Now we have to actually interact with the environment to solve it. And so there's all sorts of methods that exist. The main ones are Monte Carlo, SARSA, Q-learning, and TDN. So these are crucial ones. We're also going to do the TD lambda with eligibility trees. This is a slightly more difficult implementation, but it is important. So I'm going to cover it. So, again, pick and choose what you find most interesting, but I'm going to try to be as thorough as I can. After we've done that, that kind of covers a good sampling of a lot of traditional reinforcement learning techniques. Then we can start moving into deep reinforcement learning. And what I want to really push is that deep reinforcement learning is really not that different from regular reinforcement learning. Like, we are using a neural network, but the neural network kind of just pops in for something else that the existing reinforcement learning algorithm was doing. So there's nothing like all that new. So we're going to be able to reuse a lot of the ideas that we've explored, like the relation between all these deep Q learnings and regular Q learning is basically one-to-one. There's almost a one-to-one similarity between them. When we learn about different types of sampling methods, like our PERs, which are prioritized experience replays, we'll do another variant with a sum tree. It's basically a binary search algorithm. And then our generalized advantage estimators, the GAE and TD lambda are basically the same thing, just for different things, right? So same idea, slightly different concept. So we'll kind of see that. So we're going to be looking at value-based methods, which is the first way. Then we're going to look at the policy-based methods, mainly the reinforce algorithm, because it's very popular for this. When we do this, we will derive the policy gradient. So again, that's going to be another challenging derivation, but it is important. We will derive the entire policy gradient algorithm. And so, yeah, that'll be fun. And once we do that, then we can move into actor critic, which is a mix of value-based and policy-based. So none of these words need to make sense yet, but value-based is basically what we've talked about up till now. We don't solve for the policy, we solve for the values of different states. And then from the values, we can derive the policy. In policy-based, we derive the policy directly, right? And we can use something called policy gradients to do this. And then actor critic is just putting them together, right? We're going to have both a value-based and policy-based happening at the same time, and these models seem to work the best, and we'll talk about that specifically later. I will say, out of all of these implementations, the TRPO algorithm will be the most challenging of them. You can already take a look, because all of this, everything I'm showing here is already in my Git repo. So if you want to get ahead, because it'll take me some time to make the videos, if you want to get ahead, just go ahead and take a look at them. TRPO is the most challenging. We're going to do not a full, but a pretty thorough derivation of TRPO. It's just the requirements for TRPO requires a much higher level of optimization strategies. Like you need to know conjugate gradients and stuff like that. I'm going to try to explain it to the best of my ability while trying to keep it within the realm of understanding for most people. But regardless, about 95% of what we're doing here should be totally accessible to anyone who just has some basic math and Python knowledge. So that's the end goal. Also, I love the KISS policy, right? Keep it simple, stupid. We are not going to be dealing with fancy environments. We're not going to be dealing with like continuous. We're going to try to keep it as simple as possible, because all these algorithms I showed here can be applied to simple problems and to complex ones, right? So we're going to keep it simple, because my goal here is to explain the algorithms rather than just make it more complicated than it needs to be. But if you wanted to try a different environment, it wouldn't take more than a little bit of effort just to kind of swap in that environment for kind of these ones that we'll be looking at. So we'll be looking at the frozen lake environment here on the left, and then your lunar lander here on the right. And so these are basically the two environments that we're going to be exploring the entire time. But again, it doesn't change. If you change to a more complex environment, it doesn't change anything. It just means you have to train for longer. That's really all it is. So we're going to keep it as simple as possible. Also, my main motivation for doing this actually was so we could do a full RLHF implementation, right? Because as you can see, PPO, one of the last things we'll look at, is a key part of our alignment for language models, large language models. Like, why are large language models so good at answering questions? It's because they've been fine-tuned with a PPO algorithm. And this PPO algorithm is identical to the PPO algorithm that we're going to implement. So it's going to be a lot of fun. I was going to do this, but then I realized that I can't really just jump into PPO without actually building up to it. And I know enough people are confused about RL that it seemed relevant for me to just try to build a full course from start to end, going into some of the nitty-gritty details that long form viewers, the people that like long videos, would probably enjoy. So either way. So again, next time our goal is to tear apart the Bellman equation. We will completely derive this because it's so foundational to everything we'll do that there's really no excuse of not knowing how to get to this equation. Like, where did this even come from? We talked about intuitively what's going on, and it kind of makes sense, and you're going to see the derivation is just as intuitive for the most part. So either way, this is then the start of my full RL sequence. I am very, very excited to put this together. This has, again, all the content, all the Jupyter notebooks, everything is already in my GitHub and ready to go. I'm basically just making the videos now. This was probably 3 or 4 months in the making to kind of put all of this stuff together along with the derivations and everything. So I hope it is very valuable to you. I enjoyed really making it. But I am going to see all of y'all in the next one.